All right, welcome everybody. This is part 3 of our Navmesh to mobile VR tutorial, I guess we can call it. And today I want to have a look at orientation. So we're going to make our camera move as we are moving our phone around so that we actually get some presence inside of the world that we're in. Now, in order to do that, we need to look at 3 sensors that are built into most phones. And again, I'll let Wikipedia do most of the talking for me. There's much more in-depth information there. For us, we just need to know the sensors that we have available, and then we'll start implementing them and see how that comes together. The first sensor that is in just about every phone is the accelerometer. And the accelerometer is a little sensor that basically records the forces that are currently acting on your phone. So obviously when a phone is in rest, when it's lying on a table or it's not moving around, the only force that is working on it is the Earth's gravity, and that is most of the time the prevailing force that acts on your phone. And the accelerometer therefore is a good measurement of what is down basically. However, when you move your phone around, when you shake your phone or you do things with your phone, obviously that results in other forces that are acting upon your phone, and that obviously is reflected in the measurements of the accelerometer. Luckily for us, both macOS and Android have built-in functionality to clean up that data and provide you with a gravity vector, which is a pretty good approximation of what really is down, even when your user is moving the phone around. However, this is something that is only available if your phone has the other sensors as well. So if you have a very cheap phone that has only got the accelerometer, or what is also very common, a phone that only has an accelerometer and a magnetometer, oh, I can't pronounce that word, sorry, then that vector might not be available to you. But we implemented it in Godot 2.1.3, so provided that you do have a phone with all the sensors, you would have access to it. The second sensor is the magnetometer. I hope I said it properly this time. And the magnetometer is a sensor that measures the strength of the magnetic field that is around your phone. Now again, there's one overarching field that is always acting upon everything, which is of course the Earth's magnetic field, and therefore the magnetometer is often used as a compass, as a sensor to point to the Earth's magnetic north. However, the Earth's magnetic field is actually a very, very weak magnetic field. And there are loads and loads and loads of things around us that all have their own little magnetic field, and it all contribute to what this sensor measures. And then, of course, we have devices like the early cardboard, on which a lot of HMDs, mobile HMDs, are based, that have a really big magnet on the side of it that you can use to basically produce button clicks. And that kind of throws the magnetometer out completely. And that makes it a pretty unreliable sensor for our purposes. Now, if you don't have the next one, gyroscope, which we'll go to in a minute, and you only have an accelerometer and a magnetometer, you can combine those two and get pretty good results to orientate your phone, or get the orientation of your phone. But for our purposes today, we are actually going to skip the magnetometer. We are going to go straight to the most important sensor in your phone, which is the gyroscope. Now, the downside of the gyroscope is that only the better phones generally have a gyroscope. The cheaper phones generally don't have this. It's a slightly more expensive sensor to have in your phone, But this really is a prerequisite for mobile VR. This is the only sensor that gives you enough accuracy to really get fine measurements on the movement of your phone. A gyroscope is basically a little spinning rotor, as you can see in this little diagram here. Obviously, in a phone, it's constructed quite different than this nice little toy that you can buy in some shops. But it's basically a disk that is spinning around at high revolution. And the nice thing about that is that if you move your phone around, the spinning disk will try to stay in position. It will try to resist any rotational force of the device. So by seeing the difference, the rotational difference between your device and that little spinning disk allows the sensor to really accurately figure out what the orientation of your phone is. With one small little problem, especially in a phone where these things are quite small, the spinning disk will only resist rotational force so much. And when you move your phone around quickly, or you make huge movements with your phone, the spinning disk can't help but move alongside with it. So you'll always have something that they call drift. So you can take your phone and hold it steady, and then let's say move it 180 degrees around, and then move it 180 degrees back, and you'll see that the orientation isn't quite back where it started. Very often this doesn't matter too much, but obviously you want to stabilize that as much as possible. And we'll start looking at using the accelerometer to at least stabilize it in the vertical axes, because that really is the most important one for giving you a good sensation that you're solid inside of the world that you're in. All right, enough theory. Let's get started. We're inside Godot, and the easiest solution, I guess, should be to put all the logic inside of our stereo camera scene. But looking ahead a little bit, I am going to split out the orientation code into its own module so that you can use them independently of each other. This, again, mostly is with the idea that at some point in time you might want to build something for other platforms as well, and you want to interchange certain things. And even though the orientation code might be coming from somewhere else, you might be able to structure it better. However, if you want to all put it together into the stereo camera implementation, then that works fine as well. Okay, so the first thing that we do is we create a new script, and we are going to call that orientation.gd create. Make sure that it extends from Node so that we can use it as an autoload script and run our processes. So that's the next step. We open up the project settings, we go to autoload. If you obviously don't have selected, go to the right tab, select our orientation scripts, we call it orientation add, and that will cause that to be automatically loaded when your Godot application starts. Okay. Now we need to adjust the orientation of our device every frame, and therefore we need to enable set process to true, and that results in our process function being called. And for now, I am just quickly going to grab the gyroscope reading, because that is what we are going to start with. So every frame, we are reading our gyroscope information, and we need to process it. Our end result of this is a variable that we're going to maintain called orientation, which is a matrix 3. So a 3 by 3 matrix, which is a rotation matrix, which we can use in later on in our application, and this will always contain our original device or our absolute device orientation. All right, so we initialize that as a 3 by 3 matrix. It will get an identity matrix, which well, I think basically starts looking down. I'm not 100% sure. We'll soon find out. But obviously, we're going to start adjusting that and get to something that we can use. We're already getting our gyroscope reading. Now, our gyroscope reading is actually the weird one of the bunch. The accelerometer is a vector pointing downwards. The magnetometer is a vector pointing due north, not horizontal. Be careful with that. We might not, we're not going to be using it today, but I'll probably discuss a little bit of this at the end of the video. But if you want to use the magnetometer, depending on where you are on the Earth, it'll point slightly upwards or slightly downwards. So you have to obviously keep that in mind. But the gyroscope is giving us rotational information, and it's actually giving us a speed of rotation over all 3 axes. And that can mean that the drift that I was talking about, the orientation drift that I was talking about earlier, isn't just a matter of the gyroscope slightly drifting off center. It's also dependent on how frequent you read out the information, how accurate how accurately you are adjusting your orientation matrix. Let's say that we would, for argument's sake, be reading this every second. We would be losing all the fine steps in between of rotation. We would just be getting a single speed and applying that times a second, and that won't be accurate at all. Anyway, in order to apply our gyroscope readings, we have to create a rotation matrix out of our sensor data. So we're going to start with defining another matrix, and this one we are going to slowly put together by applying 3 rotations in order. So that's first rotating around our X, and we do the same Y and Z. So as you can see here, we're taking our sensor data, the orientation around our x-axis, our rotation around our y-axis, and our rotation around our z-axis, and we're multiplying that by the time that has passed since the last frame. And as long as we have a high enough frame rate, this should give us a really accurate rotation based on our current gyroscope settings, readings. Now notice that I am taking the x, y, and z components of our orientation matrix around which we are rotating our device. That's very important because obviously as your device physically rotates, the axes that the gyroscope measures are always in relation to the current orientation of the device. So we need to use the current orientation of our device to calculate our next rotation matrix. Now this is now resulting in a rotation matrix that is only giving us the rotation difference between our last frame and right now. So we, as a next step, need to rotate our orientation matrix with our new rotation. And we do that simply by multiplying our rotation matrix with our previous orientation, and that gives us our the new rotation of our device. And that is all we need to do just to process the gyroscope. These few lines are more than enough. We'll look at our drift compensation in a minute. But this is our starting point. I first want to show you guys what the results of this is. Now, obviously, we now need to use this. So we first of all need a function to get this information out. which we simply call get orientation, and that simply returns our current orientation. So we open up our Navmesh GD file, and let's have a look at the existing code that is here. And the important bit here is that our process in our Navmesh is actually most of the time disabled. We only enable our process if we have a path to go through. Now I'm going to remove that code, and instead I am going to make sure that the process is always running, even if we don't have a path to process. So I think I've got everything. So right now, every frame our process will be running, it will check the path size. And if it's bigger than 1, it will obviously process our path logic. But if it's empty, then this doesn't do anything. However, we want it to do something for orientation. And the thing that we're going to do here is we are going to get our current transform of our stereo camera. There we go. And we are going to update the basis, which is our rotation matrix for our transform. And we're going to update that with, whoops, /root /orientation. That gives us access to our orientation script. And then we call our get orientation function. So that will get our updated orientation, and last but not least, we are going to set our transform to our updated transform to our updated transform. That should be enough to update our camera rotation to our orientation of our phone. So let's go and try it out. For that, we need to export our package into our iOS Xcode project, and I'm just going to overwrite my data pack there. And then we need to go to our good friend Xcode, which I've already loaded up with our project, and we need to go and update our iPhone. Oh, let's wait a second until that is connected. There we go. Okay, let's go and run that. All right, I'm sharing my my screen in QuickTime, so it's all nice and black. We can see our little white divider line between our left and our right screen, but as I mentioned, our identity matrix is actually causing our camera to look straight down. So let me gently pick up my phone and see if I can rotate it around until I see. There we go. All right. Oh, it's upside down. Hold on. There we are. Okay, so we're seeing our little Godot scene there. Notice that it does flicker the frame rate a little bit. That is just the streaming of my phone to my my desktop. It's actually doing it quite well onto my phone. However, it's of course not very nice that we start our game and we are looking completely in the wrong direction. So that's going to be our next step. Okay, we're back in our orientation.gd script, and the next step is going to be applying our accelerometer data to our rotation matrix and make sure that we know what down is and we keep down stabilized. So let's start with putting our variables that we need in. The first one being our accelerometer data. But I'm also going to grab our gravity vector. There we go. Now, as I mentioned in my introduction, almost all phones have the accelerometer, but only phones that have a gyroscope to sort of extract the gravity vector will give a gravity vector out of here. So we have to make sure that that if it's not supported for whatever reason, although I guess if it wouldn't be supported, we'd be in trouble anyway for the solution. But especially if you want to extend this to support phones that have an accelerometer and a magnetometer, sorry about that, then it is handy to already have this this bit of code in. But we're simply going to check if our gravity vector is below a certain threshold, then let's go and push that threshold up here. So the gravity vector would normally be about 0.98 in length. Anybody who has had a science class would recognize that number as the strength of our gravitational field. Obviously, we're checking here if it's less than 0.1. It should be 0, but if it's less than 0.1, then we're pretty sure that we don't have that vector available. And what we're simply going to do is use our accelerometer data instead. Now, that'll do for that sort of situation. It will give a slightly more unstable result, especially if someone shakes their head around and you know, all of a sudden your accelerometer doesn't point down but points slightly sideways. But you know, what do you do? I personally don't believe that those sort of devices are really good for VR anyway. But anyway, I'll leave that to you. The other thing is, notice that I'm not doing any sort of filtering on my inputs here. When you look at a gyro, you definitely don't want to filter your gyro data. Your gyro data, you really want to use the way or the data that you get. It's generally a very stable sensor, and if you would take averages or filter that data, all that you get is more inaccuracy because of the timing involved there. Your accelerometer, we could apply a filter, but you'll see that that I actually just apply a factor when I'm correcting my my orientation matrix, and that basically has the same effect. If you are using an accelerometer together with a magnetometer to get your orientation, you definitely want to add a filter to these values, or you will get a very shaky result, and people who would use the application would get sick very quickly. But as I said in my introduction, the magnetometer is something that I'm not planning to talk about in this particular tutorial in any great depth. All right, the next thing that I'm quickly going to put in here is for everybody who is on Android. Now, I do not have an Android phone. Well, that's a bit of a lie. I have a very cheap Android phone that only has an accelerometer, so I can't use it for this at all. But I've asked around with some friends to test some of this stuff who do have a an Android phone, and at least with the default build settings for an Android phone, it looks like the X and Z axes on the Android sensor data are inverted. Now, someone else did the implementation for Android way before I got involved with this. And as far as I can see from the code, it is just giving you the sensor data as it's being produced by the OS without any alterations. On macOS, I took quite a bit of time to test different orientations of the phone and different compilation modes of the phone, because iOS has got the crazy idea that as you move your phone around and the built-in reorientation gets well, does its thing, it will actually change the axes. So there's quite a bit of code inside of Godot to make sure that that is corrected, and the values that you are getting from the sensors inside of GGScript are actually axis aligned with the access system in Godot itself. That doesn't exist on Android. And frankly speaking, I don't know if Android does anything to the sensor data as you change the orientation of the phone. It seems not to, but obviously this is all tested with the default settings of Android. So yeah, you might find that you need to tweak this more. I can't say for sure until I actually have an Android phone to play around with. So all we need to do is go and take the negative x and take the y as is, and take the negative of our z. To correct this, we're doing the same thing with our gyro, because they are also the wrong way around. Mind you, maybe the gyro I should have flipped around as well, so you don't have to make that negative here. But anyway, better safe than sorry. The other thing that I wanted to mention quickly about this is that both Android and iOS do have an API to get the orientation matrix of the phone from the OS itself. I don't know how good it is with Android. I tried to make that work on the iPhone, but I got really stuck with the iPhone. First of all, because internally Apple has flipped their axis system around, and I somehow couldn't get that to work without turning everything inside out. But the other thing which is really interesting, at least on iOS, is that the natural position for the orientation is your phone lying flat on a surface, which makes sense when you're using the phone as a phone, but which doesn't make sense for an HMD. And when you looked at some of the stuff that came out of the data, you actually get your phone gimbal locked when you are using it with their code on an HMD. Now again, I didn't get far enough with that, so there's a good chance that that with a few tweaks of the settings, that would work just fine. And if we ever get around it, we'll definitely add that as an interface to Godot. But for now, we're implementing our own little version here. So we've got our sensor inputs. We've adjusted them for Android. And obviously, again, if you have the magnetometer in there and you extend that code, you need to do the same trick there as well. We now have our new orientation, and what we're now going to do is, it does help if I correct the right ones. We were using this one. And obviously, we're going to check our length again. Actually this time whether it's bigger than our threshold. Just in case we did copy the accelerometer data in there, we have to check that again. Because obviously we don't want to apply the accelerometer if we don't actually have data. Very, very, very unlikely scenario if you're using this for VR. The accelerometer exists in just about every phone, and if it's not on your phone, you probably don't have a gyroscope either, so this code wouldn't work anyway. What we're going to do is we are going to compare what is down according to our orientation matrix with what is down according to us. So down obviously is -1 on the y-axis, and we're just going to have this little helper variable to get that. And the second thing we do is we take our gravity vector, and we are going to rotate that by our orientation. And we need to make sure that we take the normalized vector, because it's very important for the next bit that our gravity vector is in unit length, or both these two vectors need to be unit length. The next step that we're going to do is we're going to take the dot product of these two vectors. Now, the dot product of two vectors actually gives us basically the angle between the two vectors. So this gives us a I think the cosine of the angle actually. This gives us a well, an indication of how far these two are apart. And if these aren't exactly 1 or -1, we can apply this correction, which well, it'll be very unlikely that they're exactly the same, but this way we don't get any really weird flips of our axes all of a sudden. So the second thing that we are going to do, we just got the dot product, which gives us the cosine of the angle between those two vectors. We're also going to take the cross product of these, which gives us a vector perpendicular to these two vectors, and that gives us an axis around which we can rotate our orientation to correct for this. So again, just in case, we always have to normalize these vectors, or else we get issues with our code. We're going to start with another rotation matrix, and this one we want to rotate around the axis that we just calculated, and we want to take the a cosine of our dot value, which gives us the angle in radians, that these two vectors are rotated to each other. So in theory, if I would execute this, we would actually get a rotation matrix that would rotate our gravity pointer in such a way that it would equal our down pointer. But I'm going to apply a dampening factor here to just make sure that any sort of vibrations are kind of smoothed out. And it's that simple, really, to just apply that. Finally, I obviously need to apply that rotation to our orientation matrix. And now when I hold my phone upright, down is down. So I should be looking straight ahead when my phone is held upright. So let's have a look if that actually works. I probably should have a camera running to prove that I'm actually holding the phone upright right now, but I'm holding it nicely basically straight in front of my eyes. And for those who remember the scene, we had the camera quite high up. I actually would need to look slightly down to look at my my scene, but yeah, it's working quite nicely. Again, the streaming is slowing it down a little bit. On the phone, it's actually rock solid, but we can see that that this is working. All right, for those who were paying attention, they would have seen that before I just ran that test, I actually had a typo in threshold up here, but yeah, it was a small thing to correct before it actually ran, and I didn't want to sort of upset the order of this. However, there's one more thing we need to do. While we now have our orientation nicely aligned with our gravity, we need to, we now are making sure that if you are looking forward and you're sitting upright, that you're actually looking forward, so that you don't get into a situation where you start the application while your phone's on the table and you have to constantly look down to play the game. That wouldn't be very nice. However, one thing that is a bit of an issue with what we've done so far, and that definitely will become a bigger issue when we do our next video, in which I want to be able to move around the world a little bit, is that we have no control over the direction in which we are watching. So if we're unlucky, depending on what the starting orientation of the phone is before you actually pick it up and insert it into the head-mounted device, it could very well be that that we actually need to look behind us before we see our world, or or something like that. And while for some games that really isn't a problem because you just turn around and look whatever direction you want to look in to, for a game like this one, for instance, you really want to make sure that when you're looking what is forward for your sitting position is actually ensuring that you're looking at the game world and you don't force someone to have to sit backwards in order to play. Now that part of this is a little bit more work. So we'll just go through that, and I'll try and explain as much as I can as I'm writing it. I thought about doing this in 2 steps, but it really just makes it more confusing. But what we're going to do is we are going to add 2 more matrices to our code here. One is what we call a reference frame. And a reference frame is basically a matrix that is based on the current orientation of our phone to undo that orientation. So you set the reference frame at a given time when your application starts or when the user presses a button to recenter the screen. And it basically takes a snapshot of the current orientation of the phone, and it gets the inverse of it. And when you apply that to your current orientation of your phone, you get the difference of movement since that. However, if we do that straight away without any further changes, that means that all of a sudden, if you center your screen while you're looking down, then all of a sudden the application thinks that looking down is actually looking forward. So we want to filter that part out of it. The second matrix that we need is the matrix that gives us the orientation which, according to our game, is looking forward. So let's add those 2 in. So the first one is our reference frame. And again, as always, we start with an identity matrix. And the second one, is our what we call our null orientation, which is the orientation that we'll give to our application or to our logic to cell. This is what we consider being forward. Now we need 2 more variables before we can get started. First is a frame counter. And the only reason we do this is because when you first start the application and you haven't run through any of this code, it actually, well, especially because of that times 2 or .2 that we have here, it takes a few frames for the phone to actually orientate itself. So we don't want to actually calculate our reference frame until we are ready to obtain it. And that's what we're going to use this for, just to skip the first 10 or so frames before we actually set our reference frame. And as a result, we therefore also need a variable that requests our reference frame. So when this is true and we haven't had enough frames pass yet, we won't do anything. At some point we've got enough frames passed, and we will then calculate our reference frame to correct our orientation. All right, so the first function that we need is to be able to request a new reference frame. And all this does is change our reference frame request back to true. So after 10 or so frames, we'll be setting our reference frame. And for whatever reason it's not correct, the player was still busy putting their phone into the HMD and wasn't paying attention. They want to be able to reset what it is, or they've moved around really wildly and the orientation has drifted, and they want to reset it. And again, this is a problem with mobile phones, because you don't really have a very good input. You can touch the screen, and that's what we're going to do right now. We're just going to add a button on the screen to allow us to do this. But of course, with something like this, you really need a controller, and assign a button to the controller that if the user holds that button, it will reset. Now, in this tutorial, we will just use a button on the screen to get this to work. But once we are a little bit further along and we actually have our our entire game working, will actually make a difference between a click on the screen resulting in the figure moving to the location we're looking at, and holding down on our button with the one interaction that most HMDs have, will eventually reset the reference frame. But that's probably going to be not next tutorial, but the tutorial after that we handle that. But for now, we are just interested in the logic and making the logic work. The next function is obviously setting our null orientation, because this is something that our game will give our logic. And this is again going to be even more important in our next part of our tutorial when we handle moving around in our world. But for now, we're just going to get a starting position for that. So that's just a simple copy. And now we need to adjust our get orientation function to actually apply those two. And that's actually quite easy. We start with our null orientation. So the orientation that we want as being forward. We multiply that with our reference frame, which kind of undoes everything, and then we apply the actual orientation of our phone. Okay, so that's our starting point. Now we actually need to start assigning all these values. And I'm going to start with setting our null frame. So let me get my example. There we go. So obviously this is something we're going to do in Navmesh, and we're just going to do that once. On our ready, we're going to get our stereo cameras orientation or transform, and the only reason I'm getting this is because I want to get our starting location. Oh, I'm forgetting a bracket there. There we go. And we are going to go and change that. Oops, with a looking at. So we're going to update our transform so that it is looking at the center of our scene, but on the height of our camera. Because else our looking forward would be looking down towards our ground, and that's not what we want. We want the when the user looks forward, we want them to look level. When they want to look down, they have to actually be looking down. Well, that's a design choice, obviously, but that's how I am designing this today. And now it is simply a question of telling our logic what our new rotation is. Now note that I'm only sending the rotation matrix. I am not interested in the location. I needed that location for our looking at, but for our null orientation, we're only interested in our rotation matrix. We're not interested in our actual position in the world. So this is causing our set null orientation to mean that looking forward is actually looking at, straight at our scene if our user, is sitting. So looking down is looking down at our scene, looking up, looking left, looking right. It all nicely looks around our scene. But when I'm looking straight forward, I am looking straight forward at our scene. Now the last thing that we need to add in is calculating our reference frame. And for that, we're going back to our orientation.gd script. We're going all the way at the end of our process. And in here, we're going to add two things. The first is updating that frames counter, because as long as I have less than 10 frames since I started my application, I don't want to actually execute this bit of code. But if I am past frame number 10, I'm going to check was a new frame requested, then I need to go and update this. So obviously we only do that once. Once we've done that, we're happy. We're going to start constructing a new reference frame. And we're going to build that from our current orientation. Now, what I want here is I want to start with a orientation matrix which ignores us looking down or up. We basically just want to know how much we're looking towards the left or we're looking to the right. And that's actually quite simple. By filtering out our y vector from our orientation here, and obviously we need to normalize that because we're filtering out a y and that wouldn't be a unit vector anymore. Now up is up. Very easy. And then our x of our matrix becomes the cross product of the two vectors that we just calculated. Cross product gives us the perpendicular vector, which is exactly what we want. That now gives us a orientation matrix which is aligned with our current orientation, but which has taken out the downwards or upwards looking vector of the user. But we need the inverse of this for our reference frame. There we go. So if the person is currently, according to our orientation matrix, looking towards the left, we get an inverse matrix which will, center that view as if that person is looking forward. All right. Now that should be it as far as all our calculations are concerned. Obviously, we now need a button. So let's just add a button to our scene, and we're just going to put this onto our thing. Now it's lovely how that particle effect is getting there. Now that obviously is going to look very ugly in our application. This is just for the testing of this, but yeah, obviously if this was for real, we would either make this a small little icon that really sits in the corner, or as I said before, we're going to look at implementing a long click or something like that to reset this, instead of something that's in the corner of your eye that sort of destroys the whole effect. But for our demo purposes today, this is going to be enough. We're going to select our button. We are going to go to actually, let's rename that one. Reset reference frame button, and there we go. We're going to connect that up to our spatial node, which would put it on our main GD script. So this says on reset reference frame button press. That sounds good enough to me. There we go. And all we need to do here is again get our root orientation node and request reference frame. I believe we called that that function. We just need to request our reference frame. So in theory this should work. I'm going to export this out to my iPhone, and we'll be right back. Well, it won't come as any surprise to anyone that obviously we made two mistakes. The first was forgetting the up vector in our looking at, and the second one was it wasn't called request reference frame, but request a new reference frame. However, there we go. We have a working application now. Now this is exactly what we've gotten right after I start the application. So you can see that our scene is nicely centered. We are looking into the right direction, And when I'm holding my phone nice and straight, we're looking nice and forward to the middle of our scene. And when I tilt it down, then we start looking down. Now, when I started my application, I was actually looking down slightly, and well, it came up correctly. Now, to show the reorientation, I'm just going to focus on this this little side of our world, and I'm going to click on our little button, and voila, there it is. It took a minute for it to update. It's getting a bit slow, but it was instantaneous on my phone. Not quite sure why it's lagging the streaming so much right now, but yeah, every time that I use the little button, it nicely centers the screen again, as you can see, and it's keeping my my upwards or downwards looking the way it is, and it's just centering on that that lookat that we calculated. All right. Well, that's it for now. The next tutorial, we will start looking at actually navigating our world. Obviously, in VR, when you're in on a mobile phone, you don't have a controller. The only way that we can navigate is by looking around and picking a place that we want to move to. And we'll start looking at a solution for that in the next video. Hope you guys enjoyed this. I hope the sound was a little bit better. I'm using a little microphone from my phone at the moment. So I'm hoping that's better. So yeah, leave a comment, leave a like. Let me know what you guys think so far. Till next time.